Hey folks, in this video we're going to be looking at Chapter 8, Section 5, which talks about exponential growth and decay. Starting with the warm-up scenario, we're looking at a radioactive isotope that's decaying over time. It tells us that 15 grams of the radioactive isotope are being studied in the lab, and that after T days, the amount of the isotope left can be modeled by this function. So we have T is our input, our independent variable, represents time. Our unit of measurement here is days. The dependent variable, the output, is the amount of the isotope left, and this is measured in grams. We can use this function to make predictions about the future, starting with how much of the isotope will be left after 8 days. That means our independent variable, T, is equal to 8, and what we're trying to figure out is the output, A. So I can calculate that output by plugging in 8 into the function in place of T. Without a calculator, this would be as far as we can go, and we leave it here. With a calculator, we can punch this in and convert it to an approximation in decimal form. When I type it in my calculator, I find that the decimal approximation is 8.57 grams. We can also use approximations about time. So in the second question here, it asks us when will 3 grams of the isotope be left. So what we're looking for is time. What we know is the amount, 3. So if I plug in 3 for the output, I can solve this for time, T. My first step in getting T isolated by itself is to divide both sides by 15. 3/15 is going to simplify to 1/5, taking out a common factor of 3. I'm left with e to the power of negative 0.07 t. I'm going to switch this into log form by taking that base of e and moving it over to the other side. Log base e can be written as the natural log. So I get the natural log of 1/5 is equal to negative 0.07 t. To solve for t, we're going to divide both sides by negative 0.07. Leaving me with the natural log of 1/5 divided by negative 0.07. This would be the exact answer for time. To find an approximation, again, I'd have to use a calculator. When I do this, I find that the decimal approximation is 22.99, so you could round that up to 23 days. Next, we're going to look at an example of population growth, specifically the population of wolves that were reintroduced into the Yellowstone National Park. This problem tells us that in 1996 there were 52 wolves, and in 1999 there was 118 wolves. We're going to use these two data points to develop a function that models the number of wolves in the park T years after 1996. That means N naught, the initial population, is the population in 1996, which was 52 wolves. K is unknown. That's what we're going to try to solve for. K is our growth rate, or our rate of growth. And at this point, it's unknown. What we do know is that 3 years later, in 1999, the number of wolves reached 118. We can use this information to back solve for K. If I plug in 118 for N, 52 for N naught, leaving E and K. E is our mathematical constant, K is our growth rate, T is 3. I'm going to divide both sides by 52. 118 and 52 both have a common factor of 2. So if I take that out, I'm going to get 59 over 26. On the right hand side, I'm going to get e to the power of 3k. Changing into log form, I get the natural log of 59 over 26 is equal to 3k. My last step is going to be to divide by 3. You can write it as that expression over 3. You could also write it as 1/3 times the natural log of 59 over 26. And that's k. That's my growth constant. So plugging that back into my function, that means the function that models the number of wolves in the park over time is going to be equal to 52 times e to the power of this value k, 1/3 times the natural log of 59 over 26 times time. The next part of this problem asks us to use that function to make a prediction. It says, according to that model, how many wolves were there in Yellowstone in 2002? This would be 6 years after 1996, so our time here is going to be 6. We're going to plug that in for t. And using a calculator, we would solve for n. From our calculator, we get an approximation of 267.77 wolves. Okay, it says the recorded number is 272, so our function was fairly accurate, only off by a few wolves. Now onto the world of money. Money gained in an account over time based off of interest takes the form of an exponential function. And this can be really useful if you want to know how much money is going to be in your account in the future. There are 2 different formulas that we can use. The first one is if our interest is calculated a specific finite number of times per year. To find the amount in our account, we're going to take the principal, which is the initial amount in our account, times 1 plus the interest rate, and this will depend on your account, always in decimal form, divided by n, where n represents the number of times per year that interest is being calculated. We raise that to the power of n times t. Again, n is the number of times that interest is calculated per year, and then t is going to be time, and this specifically is time in years. The other formula is if our interest is being compounded continuously, meaning all the time, not on specific intervals. This equation takes the principal amount, the initial amount, and multiplies it by e. This is our mathematical constant. That's about 2.718. Raised to the value of r. This is your interest rate, again as a decimal. Times time, again in years. So we're going to take a look at this example and use one of these formulas. This example says how much money is needed to be invested now in order to obtain $5,000 in 10 years if the interest rate is 2.25% compounded monthly. So because it's compounded monthly, we're going to be using this first formula. Monthly means it's going to be compounded 12 times per year, so n is going to be 12. What we're trying to figure out is the initial amount. We want to know how much should be invested. So what we're trying to find is P, the principal amount. Other things we know, We know that we want the result to be $5,000. And we know that we are willing to wait 10 years. So T is 10. We also know the interest rate is 2.25%. We do need to convert that to a decimal. So it's going to be 0.0225. And that's our R. Plugging this into that first formula, we get 5,000 is equal to our principal amount, that's what we're trying to find, times 1 plus our rate, 0.0225, over the number of compounding intervals in a year, 12, raised to the power of n, 12, times time, which is 10. So I'm going to simplify this expression over here that's being multiplied by p. And I get 1.252, and I'm going to have to round it there. So I get 5,000 is equal to p times 1.2521 if you want to go fourth decimal place. So to solve for p, I'm going to divide both sides by that value. Leaving me with a principal amount of $3,993.29. You could use this formula to figure out how much time you would have to spend in order for your money to double, or for your money to triple, or for you to have enough money to buy the latest gaming console or maybe a new car, depending on the interest rate and the amount of times per year your interest is being compounded. Those values are going to change. You should try the problems found in 8.5 day 1, writing down any questions you have and checking with the answer key that's been posted.